week 7, potential energy and kinetic energy. And we have been talking about work and energy. Energy is the ability to do work, or if you look up in dictionary, it says vigor or capacity or the power, and that all relate to the energy. But scientifically, in the physics, energy is the ability to work. And then what is work then? And the work is the process of the energy transfer. And there are all different forms of work, and so do different form of the energy. So in the mechanical physics or in Newtonian physics, work is defined as force times distance. And then we had the work and energy theorem, which is energy gain is of an object is equal to the kinetic energy increase. So that's similar to that momentum impulse theorem. And an impulse is equal to the momentum change. Now here the energy gain is equal to the kinetic energy change. So the interpretation of this is if you have a force applied to an object, then for a certain distance, then that work is simply this times the distance. And the physics interpretation of this process is that whoever applied this force and provided the energy from their body or chemical energy turning into mechanical energy. And then through the work of force, then the energy goes into the kinetic energy of this object, or the kinetic energy in turn lost into friction between the up block and the ground. So all that is good. So now potential energy, right, are related to the kinetic energy. And potential energy is energy due to the position or shape. And so think about something that on the ground, if you lift it up to a certain height, we say it has potential energy. In particular, we say it has gravitational potential energy. Well, and that's due to the position. And then here, if you have a spring and you stretch, so its position changed. So the energy is stored in a spring. And also later on, you will learn in the molecules or some other elastic thing, if their shape change, if it is elastic, it tends to go back. But then before they go back, we say the energy is stored in a potential form within that system. So once again, energy due to the position or shape, that's called potential energy. And the concept goes, and potential energy plus kinetic energy altogether is called the mechanical energy. So now, let's do one by one. Let's figure out the potential energy due to the gravity. In this case, for example, this is a diver, and the ground is 0 of potential energy. When she climbs up, she has higher potential energy. And actually, the potential energy is determined by the mass times g. That's actually the weight times the height. So every case is you can say mgh. When a diver dives off the springboard, and she will gain speed, of course. And the physics interpretation of that process is that her potential energy is going to be lower because lower in height. At the same time, she gains speed, which is kinetic energy. So in the process of diving down, the potential energy continuously drop low, and her speed is going up, kinetic energy goes high. So that's the energy transform. If we ignore the air resistance or anything, that's the dominant part of the energy transfer. And if you wonder how she gets the kinetic energy, potential energy, excuse me, and then when she's climbing up, her body does work, which means push the work distance and the stair push her up. So the work time force times the distance, that equal to the energy transfer, and then the potential energy, more potential energy, more potential energy, more potential energy. Every step, the work is done from her body, and it's chemical energy or from the food, and transformed to the potential energy of the height. And once the height, in other words, if she climb more and more, she might need to eat more. So otherwise, she's here. So now let's solve a problem. Okay, the first one is purely a conceptual problem. What is the gravitational potential energy of the item of mass 5 kilogram and is located at 5 meters from the ground? So if the ground is here and it lifts up that much high, and it possesses potential energy. So that is simply mass times g times h. So 5 times 9.8 times 5, and in the class we get 245 joules. So that is the potential energy. Right, let's continue. We had the 5 meter high, and then potential energy we figure out from the previous slides, and 245 and 5 kilogram, and that's the potential, that's 245 joules. Now I add another question. Okay, if you release from that height, this object, when it drops to the bottom, if I ask you what would be its speed at the moment when it reaches the ground? And that is a typical problem when a potential energy or mechanical energy conservation is applied. Okay, and then so you will simply use the energy conservation. So the total energy over here on the top will be same as total energy when it's at the bottom, because assuming there's no energy loss in the friction of the air, so then we'll have the equation over here. So total energy on the top and total energy on the bottom, okay, and on the sum on top. So kinetic energy plus potential energy, that's 245 on the top, and total energy will be 0. Kinetic energy will be 0 because there's no speed. And then along the process, when it's going down, the continuously kinetic energy being increasing and the potential energy is decreasing. In fact, at every interval of time, the increase in kinetic energy will be equal to the decrease of the momentum potential energy. At the very bottom, all that potential energy is released and then all transformed to the kinetic energy. So we have this energy conservation law at work. So energy at the beginning is equal to the energy at the point, at the final point. Actually, every point along the way, you have this work. It's all the same number, the total. So we just apply this to the two ending point, beginning and the end. 245, 0. So that's the total, because on the top is 0. And at the bottom, then the potential will be 0 because the height is 0. And the kinetic energy is something we would want to find, half mv squared. If you solve this equation, there is only one unknown, which is this. And then you solve this v squared and move these two terms to the other side, and you end up with v prime is 9.5 meter per second. So to summarize what the new question talk about, we want to know the velocity when it drops to the bottom. We use the energy conservation, and then equation before and after they are equal, and we get this question, and then we get this answer. So in fact, if you had another question, what if this mass, instead of 5 kilogram, if we have 10 kilogram, the answer will be the same. You can do this practice. See, the mass increased by doubled, and also the mass in the potential energy also doubled. So in fact, if you spell them out, the mass actually cancels. The answer will be only depends on the height, and then therefore you can have a formula from here. Velocity is simply equal to the height and 2g, 2 divided by 2g. Okay, that applicable to say you want to know if something dropped from say 25 meters, what will be the velocity at the bottom? Well, you plug in its formula, 2g 9.5, take the square root. That's the maximum speed it can have. Of course, that's assuming there's no air resistance. If there is, then of course this will be reduced. Although this is not most accurate, but that's the theoretical ideal speed or the maximum speed an object will have at the bottom. All right, hope this helps. That we will continue from here. All right, let's continue on this conceptual problem. And if the height of a playground slide is kept constant, we look at the speed at the bottom. Okay, will the length of the slide or whether it has bumps make any difference in the final speed of the children playing on it? That's a question. And to picturize this, so that's the height. Okay, if a slide can go this down, and the higher speed very fast, but then if you slide down this longer distance, maybe funner. Okay, and maybe it's more exciting and go this down and up, suppose smoothly go here and has speed and in that direction, or maybe even funner if this going up and down like this. Will the final speed be the same? The answer is yes, if assume it's frictionless, which means talking in terms of energy conservation, all the energy the kid has is gravitational potential energy, which is mass mgh. So that as long as the height is the same, and then whatever history it is, as long as the energy is not losing into heat, and then the kid will have the same final speed. And exactly same question as the first question here. As long as it's 5 meters, for example, and everything, the final speed will be the same. That's what is interesting. But unfortunately, in the real world, repeat part A, assuming that the slide is not frictionless, which means there is friction. And when the kid's going down, and her body will be rubbing the surface, and there will be friction. The friction force will do work and then make the molecules and move faster. And then that will be energy we lose in terms of heat, okay, thermal energy. So in that case, if you do that, and if the longer you slide, the more friction will there be, and then there will be the longer the slide, the less the speed, because there will be potentially more energy lost in the process. So, for example, this one, and you think it will go all the way there, if with friction, and it goes here, and then loses speed, and then maybe getting stuck there because all the energy is lost in the friction, maybe. Or maybe it can matter if very smooth enough and but still has friction and go boom, and almost barely makes an old boom drop and almost down here. All right, so very slow. Okay, so that's this question. Also, we talk about our next topic with the spring potential energy, and we have a link in next page, and to simulate the spring. And spring is also a conservative force system, which means you can define the potential energy because spring follows the Hooke's law. If your displacement is to the right, then you stretch the spring, then you have potential energy. Okay, in terms of the potential energy, the potential to do work, and to let the spring force to do work. So that potential energy depends on the displacement squared, and depends on how strong the constant is, and then actually it's half k delta squared. Why is that? Because think about it. If you push this to give it potential energy, and you apply the force, but the force is follow the Hooke's law. Okay, if you begin to push, then the force is weak, so the energy is less. Okay, and then you push more, the force is more, and the whole process will require to use calculus to calculate, but you can approximately calculate. For those of you who have never known calculus, but this is the idea of calculus if you applied to this kind of situation. When you do something, actually it's simple, but the force is changing. It's not a constant force, but what do? You can get the average force. For example, half mk times delta t, that's the force, right? But that's the force of the spring constant when you stretch it. But over the process of stretching, the force is not always strong, because when you start, it was 0, and you stretch it here, it's k times delta x. Therefore, then let's take the average. 0 plus this and divide by 2. So that's where the 2 come from. Divide by 2, so that's the average force. So this is the average force during that process. Now, if the force times the distance, potentially you get the potential, the work to it. That's your work transformed into its potential energy. So it's stored in the spring. You push it, stretch it, you do work on this, and then they gain potential energy. And then let it stay there. And then the force is that, and multiply this distance again, and then you get delta x squared. Therefore, the spring potential is half k displacement squared. But no, notice the square, mathematically, it's very interesting. Now, square of any number is a positive number. Even if it's a negative number, it's still positive, because if you go that way, the force is the opposite direction. But displacement is also in opposite direction. And therefore, the work is still positive. So therefore, in either way, as long as the change in either direction, the spring potential is going up. Therefore, that's what that parabola means. So the parabola, you remember, it goes shaped like this. The equilibrium point go up and to 0 and go up like this. So that's what this parabola means. Half kx squared. That's potential. We will use this relation to solve many problems. Okay, and for those of you who want to review your calculus, and this result can be obtained by integration of Hooke's law, kx dx, and from 0 to delta x, and then you will get that as a result, and exactly the same result. Well, without calculus, you just say, well, that's the average, because it's changing the entire process, the force is changing, but we know the final result in terms of the spring potential. All right, we will continue on next slide. All right, this is the continue from previous slides, and here is the conceptual question. The kinetic energy of a system, can it be negative? And also another question, can gravitational potential energy of a system be negative? So let's answer the first question. Kinetic energy, as you recall, is half mass times the velocity squared. So positive or negative? Well, mass is always positive. Velocity, if you have a coordinate axis, you have positive velocity and negative velocity, or even a vector. But if you use a squared, okay, if you vector, you v dot v and then cosine, and you always end up with a positive number. Imagine you have velocity negative, and you multiply it negative again. In the math, we know that negative times negative again positive, obviously. Positive times positive, also positive. So something squared is never be negative, it's always positive. So kinetic energy of the system is always positive. So then A, yes. No, A, no, sorry. A, no. So because V squared always greater than or equal to 0, okay? And one idea extend from this is that if you later define temperature as average kinetic energy of all these molecules. So the temperature so defined is always positive because every molecule has a kinetic energy. The kinetic energy is positive, so the temperatures never be negative. So that is so-called absolute temperature. And that's called Kelvin temperature or thermodynamic temperature is directly tied to the average kinetic energy of the molecules in the system. And that never can be negative. At lowest and lowest, it will get 0. So, and next question, we talk about potential energy. Potential energy, as we call, is depend on positions and the shape of the object, actually the system. So, and for example, is the gravitational potential energy, so that's the ground. So let's say the distance y equals 0, and then an object over here has a height. Okay, you raise that, and it has a potential to drop, and potential energy to gain kinetic energy. So that potential energy is actually calculated by potential energy is equal to the mass times gravity. That's a gravitational force, as you recall, and because of this distance, you push it up. So if you go that, and that's positive. So now if it's below the 0 you choose, so this here below the 0 and relative to this point is negative. So potential energy can be negative. Yes, it can be negative, depending on where you choose the 0 point. In fact, potential energies always belong to two objects. So we just don't mention that. On Earth, the two objects we mention is the Earth itself and the object under consideration. So the object here. So, and actually the potential energies, this much potential energies belong to this object and the Earth, but we usually don't mention the Earth because we are on Earth. But that's, so this, in this and with that, we call it a system. Okay, whenever in physics, if it's more than one object, or especially a collection of objects, a bunch of gas molecules or gas with a piston or with an engine, and we call it a system. So I will erase this. Okay, it's a system. So system. So the energy, potential energy, always belongs to system. Here, in this particular, belong to this object and this Earth. So it belongs to both of them. But that's this much. Of course, you choose this part is be 0, and then potential energy can be above this line, it will be positive. Below this line, potential energy will be negative. So, first question, no, because square never be negative. Second question, yes, because the 0 point can be different location. Now, let's work on another question, potential energy and potential energy definition. Cap 5P9. So actually, this is problem 19 on chapter 5 of our textbook. So, and it's good that you draw a picture to begin with, read sentence by sentence. And so, 2.5 kg stone. So here's the stone, and it's held at 1.5 meter above the top of the edge of a water well. So the water well is top 1.5, and then drop into it. Boom, that's the process. Okay, what's the physics about it? The well has a depth of 5 meters, so 5 meters from here to here, so it's 5. And taking y equal 5, so we're going to use the coordinate system at the top of the edge of the well. So then that's the situation. The stone is dropped, but above the well from 1.5 meters, boom, it dropped over here, and where y equals 0. So what are we asked? Okay, and what is the potential energy of the stone earth system? Potential energy actually belongs to stone and the earth together. Of course, the earth is big, so we just say, well, that energy is all belong to the stone, which is perfectly fine for us. But we just have to, in principle, theoretically, that's just belong to the whole thing. But we're only interested in the change of this energy. But then we think that's because of the stone changed its position, so the total system energy changes. But we can think about it, all the energy just belong to the stone. That's just perfectly fine as far as our question is concerned. Now, so stone earth system, so before potential energy, before the stone is released. Okay, and that, of course, that would depend on where you take it as 0. So in this case, y equals 0 is at the bottom, and therefore the stone at climb of 5 and then plus 1.3. So the total height is 5 plus 1.3 is 6.25. So therefore it's plug in the formula mgh. That's a formula for gravitational potential energy with this 0 point. And that just multiply this thing out, you get a 12.34 joules. This means the stone held there, the total system has this much energy, okay, potential energy, which means gravity potentially will do work, and if you let it go. Now, so that's the answer for the A. Answer B, same question, when it reaches the bottom of the well, so then boom, it goes to here. What is potential energy? The question is simple. If you stick to this 0, so it's at y equals 0, so you have 0 potential energy. So then mgh, since h is 0, so at the bottom is 0. So that's done. B is 0. Now C, what is the change in potential energy? As I always say in physical science, any change is precisely calculated by the later quantity minus the original quantity. The order matters. If you do a subtraction, the later one should be in the front, okay, and then on the back. So what is the later one? So the later one is 0. So was here the early, and then later is at the bottom. So 0 change in potential energy, 0 minus the earlier one. While it was on the top, it was this number, 1234. So then you get negative 1234, the change, okay? And the negative sign means it's a loss. In fact, it goes from this high and drop to the bottom. And of course, later on we solve other problem, and this problem is the starting point. As long as it goes from here, as far as the potential energy concerned, it lost energy, lost 12.34. That's what that minus sign is for. Now, next question is spring, okay? And spring has this potential energy half kx squared, and that's potential energy we discussed in the class. Because you stretch it, it has the energy because your hands does work, force times distance. Your energy is transferred to the potential energy this time, and proportional to delta x squared. So earlier, and we relate to that, is the more fundamental idea is the Hooke's law. And the Hooke's law says the force, the returning force, is proportional to the distance stretched, or we call it extension. Okay, and some books and teachers use this extensions or x or delta x interchangeably. After all, it's how much the spring is stretched longer. And negative sign times the spring constant. Okay, negative sign means the force is in opposite direction of the extension. So if you stretch it to the left, and of course this spring force is to the positive, and if you do it right, and then the force would be negative in the positive, in the left. So that's what negative sign means. But if in this question we're more interested in the absolute value, so the absolute value of this is simply equal to spring constant multiplied with extension, which means the more extension, the more force. That's match with our experience about spring. And this constant tells you how strong the spring is. But with the same stretch, if you have stronger spring, which have a stronger spring constant, then we will have stronger force. So then we are asked to calculate A for the spring constant. So what do? We solve this. We divide this extension to the other side. The spring constant will be equal to force divided by the extension. So spring constant, therefore, will be in units of, say, 5 Newton each centimeter, or 2 Newton each centimeter, which means if you stretch 1 centimeter, you will have 5 newtons, and so on. So that's how you understand the spring constant. Okay, continuing on previous page, we talk about how do you calculate spring constant. It's a force divided by the extension. So now, in this situation, we actually have a spring, right? So, and then say we have a object with 2.5 kilogram and it'll be hanging down here. The object is actually here, and then so that's the situation. It gets stretched longer. First of all, what is the force? We try to determine the spring constant, but we have to look at the situation of this object. So a little bit messy here. So the spring is stretched here, and then it's the object, and then the object gets stretched. So object is not motion. You secure it with your hand. Is here. So it's not moving. Therefore, so there's a gravitational force pulling it down. Mass times g. Why it's not pulling it down? Because if you draw the free body diagram, there is another force from the spring, exactly what we're interested in, going up. So the reason that the object is not accelerating either way, it is because these two forces, gravity and spring, and balanced. So therefore we know that the gravitational force and the spring force has the same magnitude. That's what I put a magnitude, absolutely the value, but they are in opposite direction, so they cancels out. So that's two vector cancels out. This object stay happy. So from here, all we have to know is the gravity, and to know how strong the force applied by the spring, because it is this that cancels the gravity. So mass times g, so that's the gravity, but that's same as the spring force on the spring. So that will be 25 newtons. So this 2.5 kilogram times g, so that is both ways. Gravity is this much down, is this number, and 25 Newton up is from the spring. So these two cancels. So now we know the force is this. And then how much then? What we're supposed to do is to calculate the spring constant, right? Spring constant. So K equal to force divided by the extension, okay, which means we expand this much. Extension is given. It's stretched is 2.57, and then 25 meters. So this divided by that give you how strong the spring is. That's the spring constant. 25 newtons. You stretch this much, but it's standard units in the meters. Okay, so we convert this to meter times 10 to the negative 4, and divided by a small number, going to be a bigger number. So that's 887 newtons per meter. Okay, so of course you will not stretch the spring by 1 meter normally, but you only stretch this much. But that's how strong the spring is. Yeah, if you did stretch this to 1 meter, it would that's 800 newtons, but you stretch only 2.57, so you multiply constantly only 25 newtons centimeters. So that's how you calculate spring constant. Okay, so then let's see what we got asked. Yes, if the string was swapped, removed, and replaced by a smaller weight, okay, and then what will be the distance? How far will be stretched? Because it was stretched to 2.57. Now if we swap the weight, and this basically the half of the mass of the original one, smaller one. obviously based on your experience, it will be stretched less. So it was here, and then if you swap to a smaller 1.25, it will be less. So we are asking what would be that distance? The distance will be half, but formally you will calculate, you will use the Hooke's law again, force, but now we know this, and we know the force, which is to calculate the extension. So obviously the extension is force divided by the spring constant. You know it's going to be a half of this. Let's work it out on next slide. All right, let's continue. And same question, we're on C. If we swap the block 1.5 to 1.5, which is half of this, what would be the force? So that would be, so this was, okay, the gravity, so mass is less and G is the same. And so if that was 24 newtons, this will be something like 12 newtons. Okay, so you check something like 12.18 newtons. That was 24 because less. Okay, let's wait. And then the K we already did, so it's about 887 newtons per meter. If you stretch, if you ought to stretch it for a meter, it would be this much. But of course, you want to stretch a little bit. And in this case, with this force and with less than 24, and you only have the weight of 1.25. It's half of that. So this will be 1.883, apart from some minor differences. Now, D. Okay, the last part. Okay. Okay, actually that's B. Actually that's actually B. I just made a mistake. And actually that's C. C will be how much work an external agent do stretch the same spring to 8 meters. So now it's a simple multiplication, and you just have to do that. We got a spring constant, and then we have so once again, Hooke's law says this force equals, let me just use absolute value. Okay, K times the stretch, instead of X, stretch, extension. Okay, and then what is the extension? We know the spring constant, so then the extension, okay, how much it will stretch, and we know the spring constant. Okay, spring constant, so the force, you divide this to the other side, and then the force will be equal to the force divided by the spring constant, K, which means the stronger, the less stretch, right? And the weaker, and the longer stretch. So in this case, the force will be, oh no, we are asked to calculate the force. So then force will be simply multiplied. Then of course we just directly apply this. So it's 887. Okay, let's put the units. So this is newtons, but if you stretch that meters long, that's the units. Okay, but you multiply with the extension, but this extension only 8. Okay, centimeters, therefore 10 to the negative 2. Okay, meters. So now if you multiply this out, I would guess, okay, let me put approximately equal to, I'll leave this question to you. So I do the approximate calculation. So this is roughly 900. Okay, and this roughly 7. Okay, no, if that's 900, okay, so that's make that to 9, make that to 7. No, 9 times 8, 56. Okay, 9 times 8, 54, and 54 divided by, so it's about 54 newtons, roughly. Okay, say this is rough calculations. This is 900. Okay, that's 8. That's 100, but negative. So this is rough calculation. So this one and cancels with -2, so that's 100. These two zeros, so 8 times 9. Oh, that's 72. Sorry, my poor math. 72 newtons, roughly. So this means approximately equal to. Then of course you use your own calculation. So that's the spring constant. Once again, I write that clear. Spring constant times the extension and times 10 to the -2, converting it to meters. So your final answer will be 72 newtons. That's C. Okay, you need 72 newtons and to do. But actually, I read the problem wrong, so I just violated my own rule. You're supposed to read clearly how much work is done. Okay, how much work is done. So then, in fact, that applies energy. So the work is all turned into the potential energy. So the work is actually potential energy equals potential energy. The work equals the potential energy increase. Okay, and that equal to half. In fact, you don't have to do anything. Spring constant times extension squared, or x squared. So that's very easy. So then you half times 887, that's spring constant, and times this squared, 8 times this, times the 10 to the -2, converting to meters, and then squared. I leave the math to you. So that's how you calculate. And that's how much work is done. I didn't say how much extension, but if I ask you, okay, and one additional question. So D, okay, how much is the new stretch? Okay, it's extension with 800. How much force is this? So that'll be this. So with 8 centimeters. So I did the extra problem. And then that will be 8 centimeters, and that will be the answer will be the force is actually 72 in this case. At the end, 72 newtons roughly, or you may get 73 or 70. That's all counted right, but then the work done is this expression. So I leave the math to you. Okay, multiply 877 and 8 times 10 to the -2 together squared. All right, that ends this question. Potential energy, right, are related to the kinetic energy. And potential energy is energy due to the position or shape. And so think about something that on the ground, if you lift it up to a certain height, we say it has potential energy. In particular, we say it has gravitational potential energy. Well, and that's due to the position. And then here, if you have a spring and you stretch, so its position changed. So the energy is stored in a spring. And also later on, you will learn in the molecules or some other elastic thing, if their shape change, if it is elastic, it tends to go back. But then before they go back, we say the energy is stored in a potential form within that system. So once again, energy due to the position or shape, that's called a potential energy. And the concept goes, and potential energy plus kinetic energy altogether is called the mechanical energy. So now, let's do one by one. Let's figure out the potential energy due to the gravity. In this case, for example, this is diver, and the ground is 0 of potential energy. When she climb up, she has higher potential energy. And actually, the potential energy is determined by the mass times g. That's actually the weight times the height. So every case is, you can say mgh. When a diver dives off the springboard, and she will gain speed, of course. And the physics interpretation of that process is that her potential energy is going to be lower because lower in height. At the same time, she gains speed, which is kinetic energy. So in the process of diving down, the potential energy continuously drop low, and her speed is going up, kinetic energy goes high. So that's the energy transfer. If we ignore the air resistance or anything, that's the dominant part of the energy transfer. And if you wonder how she gets the kinetic energy, potential energy, excuse me, and then when she's climbing up, her body does work, which means push the work distance and the stair push her up. So the work time force times the distance, that equal to the energy transfer, and then the potential energy, more potential energy, more potential energy, more potential energy. Every step, the work is done from her body, and it's a chemical energy or from the food, and transformed to the potential energy of the height. And once the height, in other words, if she climb more and more, she might need to eat more. So otherwise, she's here. So now let's solve a problem. Okay, the first one is purely a conceptual problem. What is the gravitational potential energy of the item of mass 5 kilogram and is located at 5 meters from the ground? So if the ground is here and I lift up that much high, and it possesses potential energy. So that is simply mass times g times h. So 5 times 9.8 times 5, and in the class we get 245 joules. So that is the potential energy.